Hello, we are the Lear team, looking at simulation of voltage drop, thermal shock, and humidity exposure on crimped wire terminal. Our sponsor for this project was William Bond from Lear, and our team members are myself, Logan Thompson, Tim Peters, Lauren Cornell, Noah Stevens, Rachel Rosman, and Ryan Deitch.
So first, we're going to go around our project background, then go through the simulations we've done, and then progress on to our physical testing. So the project background. In short, the Lear Corporation has assigned us to take a look at some crimp connectors that they have sent us. And they are consisting of a type of brass that is crimped onto copper wire. And they asked us to make a simulation to determine the resistance increase when corrosion happens due to either thermal shock or humidity. So here you can see that's a cross section of the particular crimp connector that we're looking at. In short, again, when dissimilar metals, you can see here there is a clear brass color and clear copper color there. When dissimilar metals are in contact in an aqueous solution, corrosion actually happens. That's called galvanic corrosion. And we suspected that might be a culprit when it comes to the actual resistance drop in it. So as you can see here on the galvanic series that we've displayed in this chart here, the two metals that we're dealing with, yellow brass and copper, are just about the same on the galvanic series. So we predicted that there would be very little corrosion, if any. Yeah, you can see that because these two red bars are actually coincident with each other. The thermal shock resistance on the C260 brass, which is what the crimp connector is made of, is 57.6 degrees centigrade. And that would be the ability of the solid here to withstand sudden changes in temperature. And likewise, the corrosion expected from salt water, which is fairly corrosive, is excellent. And that is no surprise because, for example, yellow brass is used in marine environments.
All right, now switching over to the simulation side of things. First, we started off using a simulation software called ThermalCalc. So using ThermalCalc simulations, we were kind of, along with the heat treatment cycle from the thermal shock, we were able to look at how it affect a bunch of different properties, including enthalpy, heat capacity, thermal expansivity, and conductivity. Um, so you can see here the composition we used of copper, iron, lead, and zinc. Here's the definitions of all those different properties, connectivities, the degree of which material conducts electricity, for example, heat capacities, the number of heat units needed to raise the temperature. Enthalpy is a thermodynamic quantity that is pretty much the total heat of the system. Thermal expansivity is the tendency of the material to expand in response to heat temperature. So, looking at the thermal calc data, we have for the 125 degrees Celsius from the thermal cycling Lear provided us, we have 99.94% of the copper or of the brass is in the FCC phase. And then once you get to -40, you see a phase change to where most of it is still FCC, but then some is a BCC atomic structure. And so we see here, thermal calc shows us as the temperature increases or decreases, how the conductivity changes. And at around 50 something degrees, there's a shift there, and that is likely due to the BCC phase forming. Um, Thermal calc shows it if it happened perfectly instantaneously. In an actual material, you'd expect that to change more gradually because diffusion does not happen right away. So here's the results for conductivity. As temperature increases, the conductivity decreases. Thermal expansion, again, you see that kind of massive jump that wouldn't really be there in reality, but it's what the simulations show. And you see it increases until it hits about 40 or 50, like 50-ish degrees, and that has a massive drop down. For heat capacity, you have the same thing, massive drop down, so then it kind of goes up back up again. And then enthalpy is not actually dependent on the temperature, or not dependent on the phase as shown here, but does increase with temperature. Um, so then the next part of our simulations was actually trying to show that on the model. And so for this, we used a software called ANSYS Granta, which is capable of showing using a lot of different things with like the mechanical side of things, the electrical side of things, and kind of combining them together. So for this project, we use a thermal electrical conduction solver that combined with a mechanical solver, and then the license we used was just a multi-physics license we have on campus, which is important to keep in mind because our sponsors don't necessarily have all these different licenses. And so, some key notes we got from the simulation so far is that OnSys assumes ideal heat transfer and material conditions. It doesn't take into account what we would see in reality, of course. It is also, as our sponsors kind of thought and what we found out to be true, it does not be able to detect a change from cycle to cycle. So that was something we had to keep in mind going forward. And then it does detect a resistivity change from no thermal condition to a thermal condition, which was an initial concern that we ended up finding to not be something we had to worry about. Simulations are currently ongoing, so we don't have all the results here. So next, we move on to the physical testing side.
All right. For physical testing, we did the same analysis that we were doing through the simulations, moving the wire crimp connector between the furnace and the freezer at 125C and -40C respectively. And we had a 4-lead system hooked up to the wire that was being measured in order to measure the resistance of the system. And we did cycles every 2 hours for a total of 40 hours. Moving on to EBSD results. So after the physical testing, there was the resistance change that was predicted, and we compared average grain size and equivalent circular diameter of the pre and post thermal shock wire, and there was a change that aligns with the change in resistivity. Then we have our thermal cycling results from the physical testing compared with the provided values from Lear, and they are very close.
Yeah, so that's it for our project so far. We'll dive a lot further into this at the actual design expo. So hope to see you there.